I'll record this. You can use it a number of times whenever you want. You can take it. Okay. So this is my presentation. Hope it is visible now. So welcome to the experimental stress analysis class. Uh, let's talk about. I shared last class. I shared about the fundamentals of photoelasticity from the NPTEL professor. You watched that video, and also I shown some videos on some brief introduction about that photoelasticity. And you people also worked on that photoelasticity. You have done some experimentation in design lab uh, in the strain gauges as well as some photoelastic equipment. So let's see some of the definitions and some fundamental things here. So maybe it may this presentation may help you for these things. Okay, today's class we look at that residual stress, polarized light, index of refraction, photoelasticity, birefringence, stress optical constant, retardation, all these things. So, dear students, you have very rarely heard about this word residual stress. I don't know how much you are good enough to answer this question. Can even anyone know about this? Talk about this. At least one line, two line answer from your side. What exactly mean by residual stress? So definition goes like this. Residual residual stress is an intrinsic tension or compression which exists in a material. Suppose you are doing some forging operation or casting operation or whatever the operation you manufacturing something. If you are dealing with heat, definitely there is a thermal stress. If you are dealing with some external pressure, definitely there will be a compression or tensile or something bending kind of. You know how the bow and arrow works. Once you take the arrow, fix it to the bow, you pull it back. What happens? There is a compression in the bow, and what is that? The stress will be loaded here. Once you release it, what happens? It will be the arrow will go in forward direction. Just remember, some stresses are stored inside the material. Some kind of stress, it may be tensile, or it may be compression stress, or it may be thermal stress, whatever that is stress, whatever the type of stress. But sometimes it will be hidden inside the material, and during the application, during the service, when it is working, when the component is under work and it is moving or when it is rotating or something, it is when it is acting, suddenly this stress will come out from the material. It causes a lot of damage. Similarly, why this residual stress comes into picture in the optical photoelasticity? Because there are some material, photoelastic material. You know that we'll take some photoelastic, some kind of epoxy kind of material, crystalline surface, the transparent material that should be free from residual stress. If the material itself is has some residual stress, you cannot able to analyze properly in the polariscope. That is the meaning of this thing. So it should be free. How you make free when in the case of metal, you do some annealing process. Annealing process, just heat it, cool down. Whatever thermal stresses, whatever stress is there, it will release automatically. Similarly, it should happen in the glass, steel, metal, plastic, whatever it is. The stress, residual stress should be removed whenever we are taking for any analysis purpose. Otherwise, the material itself, the workpiece itself has some defects, then you cannot able to take out the good result. That's the purpose of this. So residual stress is an intrinsic or tension or compression. What kind of, it may be any kind of load stress it exists in a material without a external load being no load is acting externally, but still the material got inside internally it has got some stress. That kind of stress is called residual stress. So it should be removed properly before taking for the next procedure. That's the meaning of residual stress. So this is when there is an equilibrium between tensile and compressive stress, the glass is said to be stable. An imbalance in the residual stress can cause unexpected weakness or spontaneous breakage. Suppose you might have seen that sometimes they're going to fix the glass for a window panel. While fixing it, not because of the tool which touches the glass, once you fit it properly, if you tight it very tightly, when you fix the glass in the window frame and you tight it, okay, because of the internal stress inside the glass, okay, what happens? Suddenly a crack develops. Only it break down. Some people will tell, yeah, because of heat, it is somebody not you are not thrown any stone over that, but still it will break down. Okay, this kind of thing. So what you have to do, you should release this residual stress before taking into the consideration for or before examining the photoelastic property. That's the meaning of this. That's the why the residual stress we are talking about now. Otherwise, you don't have to deal anything about these things. So only thing you should know about what is the residual stress definition. Right. Let's go to our topic that is called polarized light. What do you mean by polarized light? You can see the diagram. You can see the diagram. Light moves through a transparent material in the form of waves. The frequency of wave form, the frequency of waveform varies with the type of light. The standard light weight of the white light through the glass is 565 nanometer. That is 10 to the power of minus 9 meter. Means, look at this diagram. This is a light source here. Can you able to see this? This question right. Now you can see this. See, the light source is a white color, right? When it is moving, it moves in all direction. This is the propagation of light. This is the property of the light. This is the white light. This it has got a property to move in all the direction, but it is moving in the forward direction. But from this, there are almost all direction. Something like you take a battery, you can see that very easily. This is a very good example. This there. See what you have to do that this property, this kind of spreading the light waves in all the direction will not be useful for photoelasticity. What we have to do, we need omnidirectional. We want only single direction. We want to take this light into only in one direction, in one plane. See, the waves are omnidirectional and vibrate out at a perpendicular angle from the direction of propagation of the light beam. We want that kind of thing. So how to make that? Let us see this. See, this is a light source. This is how it is moving. So we'll keep one polarizer here. We'll keep one polarizer. What happens? It will block all the waves. Only one plane. If you, in which way you mount it, it depends. Like if you keep it perpendicular, opposite to that, just one way, one plane of wave. See that? Only one color, one side direction, one direction, omnidirection waves are moving in this direction. So this can be done using the polarizer because if you get in all this direction, you cannot able to analyze properly. There's a purpose of the purpose we require. This is a requirement for our purpose. So how are we going to achieve that? Using the polarizer one. Similarly, in a plane or a linear polarization, only the component of light vector parallel to the parallel axis of the pole will pass through. Light may also be subject to circular or elliptical operation method. Because see, in which direction you want, you can make it. Whether you can keep it in elliptical direction. If you want like straight direction, it will move in only straight direction. Means just perpendicular. If you want in elliptical direction, it will go in circular direction. However, you want to mount this polarizer in a proper way. You want circular wave, or you want a plane, or you want a elliptical shape. All depends upon this polarizer. How you mount the polarizer. Polarizer na ಯಾವ ರೀತಿ ಮೌಂಟ್ ಮಾಡ್ತೀರೋ ಆ ರೀತಿ ನನಗೆ ಒಂದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ಬೇಕು ಅಂದ್ರೆ ಒಂದೇ ಪ್ಲೇನ್ ಅಲ್ಲೂ ಬರುತ್ತೆ ಅಂದ್ರೆ ಸ್ಟ್ರೈಟ್ ಆಗಿ ಬರುತ್ತೆ. ಇಲ್ಲ ಸರ್ ನನಗೆ ಕ್ರಾಸ್ ಸರ್ಕ್ಯುಲರ್ ಆಗಿ ಕ್ರಾಸ್ ಅಲ್ಲಿ ಬೇಕು ಅಂದ್ರೆ ಇದ್ರ ಕ್ರಾಸ್ ಅಲ್ಲಿ ನೀವು ಇದಕ್ಕೆ ಬೇರೆ ಪೋಲರೈಸ್ ಅಂತ ಅದನ್ನ ಮೌಂಟ್ ಮಾಡಿ. ಇಫ್ ಯು ವಾಂಟ್ ಎಲಿಪ್ಟಿಕಲ್ ಶೇಪ್ ಅಲ್ಲಿ ಬರ್ಬೇಕು ಸರ್ ಅಂದ್ರೆ ಎಲಿಪ್ಟಿಕಲ್ ಶೇಪ್ ಅಲ್ಲಿ ಮಾತ್ರ ಬರೋ ತರ ಮಾಡಬಹುದು. ದಿಸ್ ಇಸ್ ಹೌ ವಿ ಕ್ಯಾನ್ ಅಚೀವ್ ಥ್ರೂ ದ ಪೋಲರೈಸರ್. ಓಕೆ, ದಿಸ್ ಇಸ್ ದ ಪ್ಲೇನ್ ಆಫ್ polarized light. So if another polarizing filter is placed in the path of the polarized light beam and rotated 90 degree perpendicular to the polarizing axis of the first filter, all light will be blocked. Remember students, ಇಲ್ಲಿ ನೋಡಿ ಇಲ್ಲಿ ಮಾಮೂಲಿ ಲೈಟ್ ಇದೆ, ವೈಟ್ ಲೈಟ್ ಸೋರ್ಸ್ ಇದೆ, ಒಂದು ಬಲ್ಬ್ ಇಂದ ಬರುವಂತ ಸೋರ್ಸು, ಇಲ್ಲಿ ಒನ್ ಪೋಲರೈಸರ್ ಇದೆ, ಸೇಮ್ ಪೋಲರೈಸರ್ ಸಿ ವಿಚ್ ಇಸ್ ಕೆಪ್ಟ್ ಇನ್ 90 ಡಿಗ್ರಿ. ಇಲ್ಲಿ ಒನ್ ಆಕ್ಸಿಸ್ ಅಲ್ಲಿ ಹೋಗ್ತಾ ಇರುತ್ತೆ ಈ ತರ ಲೈಟ್ ಒನ್, ಬಿಕಾಸ್ ಇಸ್ ದ ಪೋಲರೈಸರ್ ಒನ್, this will pass in only one direction, which has where as one more polarizer we kept it in 90 degree perpendicular. What happens? This will block now. Then will not get any images, only dark field. Background will be very dark field. Remember, dark field white field patterns ಅಂತ ಇರುತ್ತೆ. ಅದನ್ನ ತೋರಿಸಿರ್ತಾರೆ ನಿಮಗೆ, ಬಟ್ ಸ್ಟಿಲ್ ಅದಕ್ಕೆ ಏನ್ ರೀಸನ್? This is the reason. See, if we keep this in the opposite direction, I mean opposite in the opposite 90 degree perpendicular, so this will block. Hope you are there with me. You are there, right?
Yes, sir.
Right. Okay. So this is how we get it. So we have to. That's the reason why they will do. They play with this polarizer. They'll keep it in different position, and we'll take it. Okay. See the second. If the second polarizing filter is rotated to an angle less than or greater than 90 degree related to the first polarizing plane, only the components of the light waves vibrating in that plane will pass through the filter. Remember, ಸರ್ ಅಲ್ಲೇ 90 ಡಿಗ್ರಿ ಎಕ್ಸಾಕ್ಟ್ ಆಗಿತ್ತು, ಎಕ್ಸಾಕ್ಟ್ ಆಗಿ ಪ್ಲಸ್ and minus is equal to 0, dark band. Whereas here we will keep it the axis less than or greater than 90 degree, not exactly perpendicular, less than or 90 degree. Then what happens? Only the components of the light wave vibrating in that plane will pass within that gap, whatever the space is there. In that, whatever the vibrating plane is there, light waves is there, that will pass in that particular gap. Hope you are there with me, right? So if you keep exactly 90 degree, you'll get dark band. If you get less than or 90 degree or more greater than or 90 degree, only that much bandwidth, whatever the thing space is there, that only limited amount of light waves will pass through that things. So that's the meaning of this. Are you there with me? Hope you are there, Venkesh, Ganesh.
Yes, sir.
Yes, sir. Yes, sir.
Right. Index of refraction. What is the refraction index? You know that. What is the refraction? I have learned this definition in the school days, PUC, all these things. What is that? The speed of a light in a different medium. Suppose the speed of light will not be same in the air medium. Speed of light will not be same in the water or liquid medium. Okay, that is the ratio. That ratio is the material index of refraction is defined as the speed of light through a vacuum divided by speed of light in the to the particular material. Maybe you are taking a material, you are passing through that air medium. That vacuum divided by material. That fraction is called refraction index. That is called refraction index. Photoelasticity, the property exhibited by some transparent solid whereby they become doubly refractive or birefrigerant when subjected to the stress. This, yeah, I shown some of the NPTEL videos. I shown how it behaves birefrigerant property. Means the refractive index will be 2. Material will be common, one material, but it shows two properties. This kind of double refractiveness is called birefrigerant material. Hope you are there with me. I have already explained these things in detail. Okay. What is that? Can you see that when a polarized light passes through a stressed material, the light separates into two wave fronts traveling at a different velocity, each oriented parallel to the direction of principal stress, sigma 1, sigma 2 in the material, but perpendicular to the each other. Can you see this? There is a light source here, light passing here, and it passes to it goes to the material. This is the material. Where this material, this at this point, I want to find out the stress, point of interest. So it is stressed, it is under stress. So what happens when it passes? There are two components. One is sigma 1 direction, one is sigma 2 direction. So if you find this value and this value, I can able to tell what exactly the stress developed in this material. How we are going to identify? Using, I told that there is a stress optic law or Snell's law. From that there is one equation. Using that equation, I can find this is the direction of the stress. This is the direction of principal stress. This is the maximum stress. This is the minimum stress, something like this. So this is how we are going to find out the stress using the light. Here, light is a sensor. I told that yes, I am recalling the words which has been used in NPTEL. Here, light is the sensor. When it passes through a material, this material is under load. It creates this light wave split into two waveforms. Okay, in a different velocities. Okay, this gives the sigma 1 and sigma 2. Birefrigerance is a result of stressed material having two different indices. That is two diffraction index. That is N1 and N2. In most material, the index of refraction remains constant. However, in glass and plastics, the index value varies as a function of stress applied. See, this is the beauty of the subject. We are not taking any metal, aluminum, copper, steel. We are not using it for electricity. What we are using only glass and plastic. What is the plastic? Epoxy plastic. That is photoelastic material. That is epoxy, the circular small specimen. That is epoxy plastic polymer. Only these materials have this kind of property. What is the property? By refrigerance property. If you load it, it behaves in a two it shows two index, refraction index. When it is stressed, when you stress that material, it behaves in a different. When you release it, it will behave. So based on the stress optic law or Brewster law, you're going to find the what exactly the stress in that particular material. So this is the core. This is a why. Yeah, this is how we're going to find out the stress using this. So what is the stress optic law says? N1 minus N2, that is refractive index. Yeah, 1 refractive index 2, that is equal to CB into sigma 1 minus sigma 2. This is the refraction index. CB is stress optical constant, Brewster constant. This is the constant of a material. Okay, this is the refractive index of the material in one direction, refractive index in the other direction. So we can find using this equation. This is a principal equation. This law established that birefrigerance is directly proportional to the differences of principal stress, which is equal to the difference between the two indices of the reaction N1 minus N2 exhibited by a stressed material. Therefore, birefrigerance can be calculated by determining the delta N. So, there is an equation for this. You will find out delta N. Okay, by using the different constant of the material, we are going to consider the material constant. We are going to take the material refraction indexes and sigma 1, sigma 2. Then this retardation value, that is sigma delta divided by T. This the thickness of the material also be is very much important here. So T stands for thickness of the material. So retardation, nothing but the phase difference between light phase difference. There will be change in phase, right? Frequency, crust and tuff, that one cycle, that phase, okay, that is represented by delta. That velocity differences is delta. Delta divided by thickness of the material, that gives the retardation value. Retardation means delta n value. So retardation of polarized light through a stressed material is a light source, and the plane polar because one polarizer will be there. Because of that, see when you see this one single sided armor, you should tell that it's a plane one side. The light waves is going in one direction. When it hit this material, when it passes through this stressed material, there will be two component, sigma 1, sigma 2, sigma 1, sigma 2. This differences in the phase, this is called, can you see this, the differences in the phase is called retardation. Explain the formula is difficult, but when you look at the experimental part, this phase difference is called retardation. So this is how we get it. Retardation value is this is delta. Right. So how stress is calculated? Stress is equal to retardation divided by thickness into stress optical constant. Stress optical constant means how you got the stress optical constant. See, we got it from the stress optical constant. So this CB. This is a material. So using this equation, you can find the stress. You can find the stress. So the equation comes like this: sigma is equal to stress divided by thickness into a constant value, retardation into this value. So you'll get the stress equation. So what are the principles of photography? The instrument designed to observe objects under the polarized lights are called polariscope. The scope, the instrument, that is the arrangements of polarizer, lens, light, all these things are called polariscope or strain weavers, because dear students should think that always in the experimentation part, we are not directly measuring the stress. In all our experiments, we are measuring strain. From the strain, we are measuring the stress. I think this is a fundamental thing you should keep in your mind. If you observe very keenly, if you take any NTM lab, MT lab, or design lab, we are measuring the strain, deflection, change in length, then we are converting into stress using Moore's law or whatever it is. Okay, there is no instrument directly which measures the stress. Hope you are there with me. This is a this is how in the eighth semester you can realize there is no material means there is no the equipment in your laboratory to measure the stress directly. We are measuring the stress from the strain. First, you are calculating change in length in the tensile strength by the original length. Then you get the strain. We will know the Young's modulus value of the material. Then we calculate the stress. This is how you do. Similarly, leave that. We are going to view this in a polarized scope. We fix the material. We pass the analyzer. We keep the polarizer. All these things analyze the material. Then this arrangement is called polarized scope. Okay. So this arrangement already we know that you have conducted some experiments here. So principle of by rotating the second polarizing filter, this is the second polarizing filter. This is the first filter. See from the light source, first filter will get only one direction. Right? It passes through a material. It splits into two. Okay, you'll get the retardation value. You'll find out. Then one more analyzer you keep it. How you keep it? It depends upon your requirement. Whether you keep it 90 degree, it will block. You'll get full dark image like this. If you keep it in somewhere less than 90 degree or greater than 90 degree, you'll get only that path. See, by rotating the second polarizing filter, this one, the user can control the amount of light allowed to pass through. That's how you make it. You have some small opportunity. You just recall that the experiment all set up. You are going to rotate that lens, right? Analyzer. One way there is a one circular. There is some scale over these things. There's some of degrees amount fitted over or calibrated over these things. You just rotate this analyzer. ಮಾಡಿದ್ರಿ ಸರ್ ನೀವೆಲ್ಲ ಜ್ಞಾಪಕ ಇರಬೇಕು ನಿಮ್ಗೆ ಈ ಕಡೆ ಒಂದು ಲೆನ್ಸ್ ನ ನೀವು ಸ್ವಲ್ಪ ಮೂವ್ ಮಾಡಿದಾಗ ನಿಮ್ಗೆ ಯಾವ ಪ್ಯಾಟರ್ನ್ ಬೇಕು ಎಷ್ಟು ಲೈಟ್ ಪಾಸ್ ಮಾಡಬೇಕು ಅನ್ನೋದು ನಿಮ್ಗೆ ಗೊತ್ತಾಗ್ತದೆ ಈ ಎರಡು ಅನಲೈಸರ್ ಸ್ಟ್ರೈಟ್ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ 90 ಡಿಗ್ರಿ ಇದ್ರೆ ವಿಲ್ ಗೆಟ್ ಓನ್ಲಿ ಡಾರ್ಕ್ ಬ್ಯಾಂಡ್. If you rotate it little bit less than 90 degree or greater than 90 degree, you can see some of the colors here. The components here, that's what they tell here. By rotating the second polarizer filter, this one, the user can control the amount of light allowed to pass through. Are you there with me? Are you there with me?
Yes, sir.
Yes, sir.
ಅಂದರೆ ಎರಡು it can ನಮ್ಗೆ ಎಷ್ಟು ಬೇಕೋ ಅಷ್ಟು ಲೈಟ್ ನ ನಾವು ಇಲ್ಲಿ ಪಾಸ್ ಮಾಡಬಹುದು. How? By rotating this. We have got some facility there to rotate. I think you can recall the experiment. The components of the two light waves that to pass through at any given angle of analyzer of rotation interface with each other, resulting in a characteristics of color spectrum. ಅದೇ ಇದು 90 ಡಿಗ್ರಿ ಇದಕ್ಕೂ 90 ಡಿಗ್ರಿ ಲೈಟ್ ಬಿಟ್ರೆ ಫುಲ್ ಡಾರ್ಕ್ ಬ್ಯಾಂಡ್ ನಿಮಗೆ ಬ್ಲ್ಯಾಕ್ ಬ್ಯಾಕ್ ಗ್ರೌಂಡ್ ಬರುತ್ತೆ. ಸ್ವಲ್ಪ ಕಲರ್ ಚೇಂಜ್ ಮಾಡಿದ್ರೆ ಈ ಕಲರ್ ಬರುತ್ತೆ. ಇನ್ನು ಸ್ವಲ್ಪ ಮಾಡ ಈ ಕಲರ್, ಇನ್ನು ಸ್ವಲ್ಪ ಮಾಡ ಇದು ಯಾವ ಕಲರ್ ಬೇಕಾದ್ರೂ ಜಸ್ಟ್ ಮಾಡ್ಕೋಬಹುದು. ದಟ್ಸ್ ದ ಮೀನಿಂಗ್ ಆಫ್ ದಿಸ್ ಥಿಂಗ್. ಸೊ intensity of the color displayed when stress transparent of a transparent material is viewed under polarized light is modulated by the retardation. Of course, each integer multiplied with standard wavelength light, that is 565 nanometer for glass, 570 nanometer for plastic. ಈ ಎರಡೇ ಮೆಟೀರಿಯಲ್ ನಾರ್ಮಲ್ ಆಗಿ ಯೂಸ್ ಮಾಡೋದ್ರಿಂದ ದಿಸ್ ಇಸ್ ಅ ಕಾನ್ಸ್ಟೆಂಟ್ ವ್ಯಾಲ್ಯೂ ನಮ್ಗೆ ಗೊತ್ತಿರುತ್ತೆ ಇದರಲ್ಲಿ. Because only these two either you use glass or we will use 99% we will go for plastic because you can use a number of there's a purpose of this thing. 570 nanometer is called fringe value. Fringe value means n. The intensity of the color diminishes as the retardation of the fringe order increases. That's what when you move the analyzer, you go closer to 90 degree perpendicular, you will get it diminishes. Diminution means you will get black background. See, black background 0, yellow, red, first order, blue, green, yellow, red. This is first order. Green, yellow, red, green, second order. Green, yellow, red, third order. Means yellow, red is one order. Blue, green, yellow, red. Blue, green, yellow, red. This is first order. Green, yellow, red, green. Green, yellow, red, green. Second order. Okay, like this. You can. This is the order of fringes. Okay. So these color patterns visible when using polarized light can be used to observe and make a qualitative evaluation of the stress in an object. This method is very subjective and requires experience and training. Of course, you cannot do it in a single attempt. You cannot tell that I'll find exactly. Once you do some trials, 1 or 2 trials, and you should be master in that, and mounting, fixing the polarizer, analyzing, weaving it, okay, and you should check whether it is we are doing in a proper method. All this requires skill and expertise. A quantitative measurement of residual stress can be obtained using a polarimeter, an instrument that measures the retardation, which is proportional to the stress. Of course, I told the importance of residual stress. It should be free whenever you are using the material. So the retardation value, once you measure it using a polarimeter in a n number of times, then you can tell that we should, before taking the photoelastic material for weaving that, the material should be free from the residual stress. Plane polarization and circular polarization. To determine the direction of principal stress in a sample, a plane polarization technique is typically used. To do this using plane polarization, it is important to first orient the sample such that the point of interest, that is POA, that is exhibit minimum light intensity. Means I've shown some of the diagrams here. I'll just go to this. This is, see, this is the point of interest, POI. So when I have to use this, I should first select which is the point of. I want to find the stress here, or here, here, here. But make sure that once ever you fix it and you apply some load over the material, this light rays should pass inside. This rays should go inside this material. If the point of interest is here, and if the light passes here, then it's of no use. Means this whole material should be under the plane for a light. That's a that's what it says. Okay. So next, in this orientation, a direction of principal stress at the point of interest, either x or y, will be parallel to the axis of the analyzer polarizer, and all these things are shown that sigma 1 and sigma 2. Rotating the sample 45-degree places the sample in a proper position for measurement. I think you remember that whenever you're doing experiment, we rotate that in a very 45-degree, you're going to check. Slowly, you rotate that analyzer 2 to a 45-degree, then we'll check the patterns, like different color patterns. See, this is the first plane. See, I will go before that. We'll read this principle of photoelasticity. Using circularly polarized light, the measurement is independent of the direction of the principal stress at the point of interest. To change a plane of polarimeter to a circular polarimeter, two quarter wave plates are added to the light path as shown below. To change plane polarimeter to a circular polarimeter, see, whatever you saw here is a plane polarimeter. It's just a plane polarimeter. If you want to make it to a circular, I'll share this PPT. You can go through that once again. To change the plane polarimeter to a circular polarimeter, I want in circular direction. So what I'll do, I'm adding some extra. What is that? This is our first quarter wave plate. First 1/4. 1/4 ultimate quarter. First quarter wave plate. Second quarter wave plate are added to the light path as shown below. This is how we keep it. This is how we convert from plane to circular. What happens? See here, the light waves in single direction, it passes through this. Okay, this is a phase difference will be there because this is the first quarter plate. Okay, then it will go to the point of interest. This is a material which has been stressed. Once again, it goes to the point second wave quarter plate. Then you'll get a once again there is a phase difference. Then you'll keep it in the see here. Now you get the waves. You're keeping in this direction. When you are converting from plane to Circular means here the circular wave will pass. Circularly it will pass in this material like this in circular pattern and it will come out from the analyzer. So the relation used for calculating the retardation of polarized light transmitted to a stressed material is this is a formula sigma x or sigma 1 or sometimes we will call it a sigma x and sigma y because x and y direction is there. Delta it is the retardation, it's a constant of the material. T is the thickness of the material. X and Y are the principal stress, sigma 1 and sigma 2. So measuring technique, let us see that, then you will understand that some of things. So when you look at, you'll get the strains. When the material is loaded, you see the pattern like this. So from this, you can examine that where exactly the stress is more, where exactly the strain is more, how you can reduce the, how should we change the design pattern. Then we'll analyze. So white light produces a complete spectrum of a light. This includes the visible spectrum. Of course, normally we use white light in the this base source. Okay. The intensity of the light is modulated by the retardation exhibited by the sample. That is, we know that from using quarter plate, we are going to do these things. So results are highly subjective to the interpretation, can only be used qualitatively. These require a lot of skills. This requires a lot of skill. So I've seen some colors. Do you think that Do you think that, sir, can I'm measuring in a proper? No, you require a lot of expertise. You require a lot of training. You cannot tell, sir, I got some colors. Then it should be some. No, you cannot tell like that also. So it requires a lot of skills. Can only be used for qualitative measurement. You cannot directly tell what are the result you got it. Oh, this is exactly like this. You require some qualitative measures. Once again, you have to recheck with some formulas. They'll use some compensators to check. They hold it, they'll observe it very keenly. They will tell which part of the material has gone to showing a stress or strain, all these things. See, compensator method, the simplest method of measuring retardation. Compensator is a calibrated handheld device, something like some small scale kind of thing. There are our plastic scale that optically adds a retardation of equal but opposite signs to the sample. They'll keep it on this and see that there is one more scale. Under that there is a crystal material. There is a photoelastic material. Over this scale is the compensator. You look at this compensator and you measure the value. The net result is a light intensity of 0, which is easily recognized visually as a block in the color pattern. See, this is a pattern. See, they look at very keenly and they will tell for another more details. For extra details, they will collect it from this compensator. There are two types of compensator. One is babinet or wedge, which is something like a scale readout. What you see here is a babinet. Nowadays there is some digital readouts. There is a double wedge. Okay. Now automatically the digital will there is something like a digital screw vernier scale, something like this. Okay. So this is one analyzer method. Analyzer method. I think you remember that in BTL video how they use. There are two, three methods analyzer. See, they'll keep it the material here. They'll analyze from the microscope. They'll show from the microscopes. So shall I continue or shall I stop here? I got only 3 slides. Shall I continue? Finish it? Venkatesh?
Sir,
Okay, then. Thank you. Analyzer rotation method. The analyzer rotation method uses a circular polarimeter setup as shown below. This is called the Tardy method. When only one quarter plate is used, this is called Saramount method. Means here there is no two quarter plates. Here the analyzer rotation method uses circular polarimeter setup. Circular polarimeter means this is a one plane polarimeter. From this quarter plate, dump the material, it will go to the second quarter plate. Here it is existing. Here they'll keep it in a circular axis of polarization is just perpendicular to this, means just opposite to this here. So here what happened? They use this when only one quarter plate wave plate is used. It is called Saramot. If you use only one quarter plate here, see, instead you remove this, just if you mount it one quarter plate, then it is called analyzer rotation. You want to rotate and you should Check this. If you keep two here, actually in the figure there is a two here by mistakenly. Don't get confused. Okay. The second wave plate will not be there. Okay. If you keep only one only one retardation, that is one quarter plate, then it is called Saramount method. So the analyzer rotation method is generally used to measure the fractional levels of retardation. The sample is first position. There are a lot of these are some of the different types. No need to worry about this analyzer rotation method, all these things. Only thing you know to about the plane polariscope and circular polariscope means circular means there will be two plates here. That much you remember. These are some of the extra things that are there in the PPT. We'll see that later. See this kind of scale you are seeing in the devices. So we are going to rotate this analyzer. Okay, retardation is calculated from the fractional fringe order that is read directly from the dial. See that? First you keep it, then you rotate it, then you take one more thing. Like this, you calculate the retardation value from fringe constant. Fringe value of fringe constant ಎಲ್ಲ calculate ಮಾಡಿರ್ತೀರ ಅದೆಲ್ಲ ಗೊತ್ತಿರುತ್ತೆ. So using the same fringe means that is value, the delta value you get it from the retardation in nanometers. Stress will be calculated directly. You know the thickness of the material, you know the constant of the material. That is, then you substitute these values, you will get the stress value directly. So, example, retardation value is 509 nanometer, thickness is 6 mm, that sample. CV is 2.5 for plastic. So, directly measure it, you keep this value, you'll get it 33.4 megapascal. Means at the point of interest, at particular that point, 33.4 megapascal of stress is there. Clear? So, this is how they calculate the stress using the photoelasticity. Any questions from your side? Any questions?